Go to question 3. Right. It says 200 volts RMS. What is RMS? Root means square value. RMS. 50 hertz sinusoidal main power supply is connected to a primary coil of a step down transformer with turns ratio 20 to 1. With turns ratio 20 to 1. Right. Then the secondary coil feeds a full wave bridge rectifier with ideal diodes, followed by a smoothing capacitor C and a Zener diode voltage regulator as shown in the circuit diagram. Right. Now, to answer this type of question, overall you have to know all the electronics. Right. Overall you have to know all the electronics. You have to have a good general idea, good idea about electronics. But if you know everything, easily you can write. Right. That's the thing. If you know everything, easily you can write. Right. But if not, right? Sometimes you might get stuck in the middle of the question, right? Then 3. Then it says circuit diagram, right? Now the circuit is given, and basically once we saw the circuit, right, what should comes into your mind is our rectifier circuit, full wave rectifier, right? What should come into your mind is full wave rectifier, right? This is the exact same circuit as the full wave rectifier, right? Let's see. First one, calculate the RMS. Calculate the RMS, VRMS, voltage and peak voltage VP across the secondary of the transformer. Take root 2 as 1.4. Okay, then RMS is asked. What is given here? 200 volts. That is also RMS. Right? 200 volts is also RMS. And VRMS is asked. Right. So we know VRMS equals Vmax. Vmax means VP. Both are same. Vmax, maximum value or peak value. VRMS is Vmax over root 2. VRMS is Vmax over root 2. Right? Then VRMS given here is 200. VRMS given here is 200 equals Vmax. Right? Vmax is also called VP. Right? Then this is Vmax over root 2. Now Vmax of this first coil is 200 root 2. Vmax of the first coil is 200 root 2. Right. Now using the transformer, you can find the output voltage or the V2 of the secondary loop, secondary coil. Then equation of a transformer is this, right? The equations V1 no V2 equals N1 no N2 for a transformer. V1 no V2 equals N1 no N2. Then V1 is 200 root 2, right? And I'm going to find V2. N1 to N2 ratio is given as 20 to 1. That is given as 20 to 1, right? Then 20 simplified, 10 remains. Then it says V2 equals 10 root 2, right? Now we need RMS value at the secondary coil. No? Again, VRMS equals Vmax over root 2. Then VRMS equals Vmax for the secondary coil is 10 root 2 over root 2. Root 2 cancels. Then VRMS equals 10 volts. Final answer 10 volts. Right? VRMS equals 10 volts. And then VRMS voltage and peak voltage VP. And VP is also asked. VP is here. VP is we do know. Then VP equals 10 root 2, right? 10 root 2 is given as 1.4. That is 14 volts. Right? 14 volts. Right? Well, first calculations are these two. First two are these two. Right? RMS calculations. Second one. Draw the shape of the voltage waveform at the output of the full wave with rectifier without the capacitor and Zener diode. Right? Without the capacitor. If there is without the capacitor, there is no smoothing. If there is no capacitor, there is no smoothing. If there's no capacitor, there's no smoothing. If there's no smoothing, right, what happens is only the rectification takes place, right? Rectification, rectifier with and there's no smoothing. Then from the rectifier, right, this is how the input voltage is rectified, right? Now these are the parts we have covered in theories. These are the parts we covered in theories. Otherwise, now you can't do all the things when the question is here. Right? You have to know the shape. But that is not the thing when it comes to questions. Right? That is not the thing when it comes to questions. And when you draw this, minimum, you have to draw like 4 loops. Minimum of 4 loops. Minimum. Right. Then 3. What is the frequency of the output voltage of the full wave bridge rectifier? Right. Now, if I give the idea here, right, the input signal variation is like this. No, input signal variation is like this. We have drawn all these things in the note, right? Input variation is like this, right? Now here it says the frequency is 50 hertz. It says frequency is 50 hertz, right? Now when there is rectified, what has happened is something like this. No, now the vibration is only this. And during the same time interval, now 2 vibrations takes place. Now initially it was only 1 vibration. See? That was only 1 vibration, 1 oscillation or 1 vibration. And now it is 2 vibrations during the same second. Now initially if it was 50 hertz, now it should be doubled. That is 100 hertz. Right? To get the idea, I just showed you these curves. Right? So therefore here it should be 100 hertz. Answer for the third one is 100 hertz. Number of loops are doubled over the number of vibrations. Number of oscillations are doubled. Since number of oscillations are doubled, right, frequency is doubled. Frequency is number of oscillations, so number of vibrations per second, no? Right, that is a per second value. Next, 4. How a full wave rectifier different from a half wave rectifier? In half wave rectifier, right, the output you are getting is this. In a half wave rectifier, the output we are getting is this, right? Like this. Exactly half of the wave is cancelled off, right? Exactly half is cancelled off. Then the question is about how full wave rectifier is different. Then what's the difference? Difference is both halves are utilized here, right? No half is going to cancel, right? No half is going to cancel. Both halves are utilized. Then write down both halves of input signal is utilized in full wave rectifier. Whereas only one half of the input signal is utilized in half wave rectifier. Right? So that's why we call it full wave and half wave. Right? That's why we call it full wave and half wave. That's the exact reason behind identifying it as a full wave rectifier and a half wave rectifier. Right? That's the thing. Right. Next. 5. Calculate the mean value of DC voltage, VDC of the rectified signal. Take VDC equals Vp into 0.65. Right. The equation is given. Nothing to do. VDC equals Vp 0.65. Right. Vp is found as 14 before. No? That was 14. Right. Then 14 into 0.65. Right. That is 9.1 volts. 9.1 volts. 9.1 volts, right? Then part B, right? We are moving on to part B. Part B, right? If the load resistance RL is 400 ohms and the Zener voltage VG is 8 volts, calculate the current IL through the load resistor, right? Zener voltage is 8 volts. If the Zener voltage is 8, right, we know when this Zener diode functions in the reverse bias state, right, this keeps this 8 volts across the Zener diode, no? It keeps the Zener voltage across the Zener diode. This RL is now given as 400 ohms, right? RL is given as 400 ohms. Then, if I need IL is the current through RL, no? Right? See how easy? IL is the current through RL. Then, to get IL, apply delta V equals IR for RL. Then, for RL, delta V equals IR. Delta V equals IR. Then, delta V is 8. Right? We need IL. R is 400. Then, IL is 8 over 400. 8 over 400. 8 over 400 means if there is 802, which means 0.02, right? Right, which means 0.02 amperes. 0.02 amperes. Right? Simple as that. Simple as that. Then IL, that's it. Part 2. This is part 1. Right? Part 2. The ripple voltage VR. Ripple voltage. Ripple voltage means in rectifiers, right? When the ripple is formed, right? The ripple voltage means the voltage difference between the ripple, right? Voltage difference between the ripple. The ripple voltage VR is given by VR equals IL over FRC, where IL is the load current, FR is the ripple frequency, and C is the capacitance of the smoothing capacitor. If capacitance of the capacitor is 200 microfarads given, 200 microfarads, calculate the expected ripple voltage, right? Then all other values are known. Then VR equals IL over FRC. IL is 0.02 from here, right? IL is 0.02 from here. And FR, we found the frequency as 100. And capacitance is given as 200, that is in micro 10 to the power minus 6. Right? Simplify. Right? 2 cancels off. And 10 to the power minus 6. 4 minus 2. Minus 2 to minus 2 also cancels. It is coming as 1 volt. Right? Ripple voltage is 1 volt. Ripple voltage is 1 volt. And by the way, this is the last year question, right? Sometimes you might have seen, right? I couldn't tell you. This is the last year question, no? This is 2025 A level, 2025 A level essay, electronics essay, 25 A levels electronics essay, right? So we are discussing the last year question here, right? And some students are like saying that, or they are thinking that what we call the rectifier. Rectifiers are not asking. See, now the last year, this entire essay is from rectifiers, right? The reason was there were like not much questions from rectifiers in the recent years, right? Then some students didn't practice the rectifier, right? And sometimes even some in classes also, right? Teachers also, they didn't teach the rectifier because they are thinking the rectifier is not coming, right? But now last year, this entire essay was given from the rectifier, right? So therefore, when it comes to question patterns, we can't say anything, right? We can't say anything about question patterns. It can be different, right? As professors wish, right? It can be different as professors wish, right? Because they can do anything. They can do anything. That's the thing. Now, from our side, what you should do is you have to practice all question types. Otherwise, without practicing the question types, if you are just planning to sit for the exam, right? Then it will not be effective, right? Will not be effective if you are planning so, right? Practicing all question types is the safest way to do this from our side, right? Then next ripple voltage. Okay. Then part 3. Part 3. Part 3. Draw the shape of the expected voltage waveform of the rectified output after smoothing, indicating maximum and minimum voltage values. Right. Now ripple voltage is 1. Right. After smoothing is asked. Right. See. Then V out with time. Right. V out with time. Now what happens is, now our initial shape was this, no? To show you the exact correct shape. If I get the guidelines from here, right? See, if I get the guidelines from here, now peak voltage is 14, no? See, peak is 14, peak is at 14, then this is at 14 volts, and ripple voltage is 1 volt, which means that is going to drop up to, 1 volt, right? See, that is going to drop up to 1 volt, then 13 volts. So the final shape is like this. Final shape is like this. Final shape is, now it is reaching the peak and dropping up to this level only. Dropping up to this level only. Right? And this gap in between, oh wait, this gap in between is connected by the capacitor. This gap in between is connected by the capacitor. Capacitor variations are linear. Then this is a linear part. This is a linear part like this. And again, from here to up to 13 it drops. From here to up to 13 it drops. From here to up to 13 it drops. Right? This black colored one is the expected voltage variation. Right? Now in the class also we have drawn these ones. Right? Now in this question, something is given as a ripple voltage. Right? That's the equation given for us. Then using that ripple voltage equation, then we have to adjust ourselves and do this. Right? So this is the expected curve. This is the expected curve. Right? So likewise, you have to be kind of conscious and very mindful about these things. 4. 4. What will be the ripple voltage if the capacitance of the capacitor is doubled? Right. If the capacitance is doubled, what happens is, right? If the capacitance is doubled, right? What happens is, we know capacitor functions from Q equals C, we know, right? It functions from Q equals CV. It functions from Q equals CV, right? Now this is only about ripple voltage, right? Yeah. If there is only about ripple voltage, you can argue using this also, right? Because this equation was given. What is the equation given? What was the equation given? VR. Ripple voltage is IL over without changing anything else. If capacitance is doubled, simply if capacitance is doubled, VR is halved. Right? If capacitance is doubled, VR is halved. Right? So therefore, ripple voltage is halved. Ripple voltage is halved. Ripple voltage is halved. Right? Ripple voltage is halved. Next, part C. Part C. C1. Describe how to regulate voltage using a Zener diode. Right. Describe how to regulate voltage using a Zener diode. So we know Zener diode functions as a normal diode when there is in a forward bias state, and Zener diodes function as a voltage regulator when they are reverse biased. Right. So what happens is, when they are reverse biased, right? When they are reverse biased, it flows a leakage current through the Zener diode by keeping a constant voltage difference across the Zener diode. Right. Since it keeps a constant voltage difference across the Zener diode, voltage is regulated. Right. Write down. Write down. Write down. When it functions, when it functions in reverse bias state, in reverse biased state, when it functions in reverse bias state, right? It flows. It flows a leakage current. It flows a leakage current through Zener diode, and keeps and keeps a constant voltage difference and keeps a constant voltage difference across it. So voltage is regulated. So voltage is regulated, right? So voltage is regulated. So likewise, write a complete answer. Right? So you know these related theories, no? And when you answer, make it complete. Write it as a complete answer. Right? Otherwise, don't write like what we call the partial answers or the incomplete answers. No marks will be given. Right? See, one is done. Then second one. Given the ripple voltage value obtained in V2 above will smooth using drop below. Given the ripple voltage value obtained in V2 above, will the smooth voltage drop below 8 volts? If so, is the regulation still effective? Give reasons for your answer. Right. So what they ask is, will this ripple voltage go below 8 volts? Right. That was 13. So it won't go below 8. That is 13. No. No. Right. That is no. Right. That is no. And will there is effective? Now about the Zener diode, this is what you should know. Right. This is what you should know. If Zener diode, if the voltage difference across Zener diode is less than the Zener voltage, right? If the voltage difference across any Zener diode is less than the Zener voltage, it won't function. Right? If the voltage difference across the Zener diode is less than the required Zener voltage, it won't function. Right? That is the thing. It won't function. Then, if the voltage difference across the Zener diode is greater than that Zener voltage, it will function. Right? It is effectively functioning. If not, it won't function. Right? Simple as that. Right now, it doesn't fall beyond 13. No, it doesn't fall beyond 13, which means that is always above 8. Since that is above 8, Zener diode is always functioning. That is always effectively functioning. No, the reason is uh, minimum output voltage. Is 13 volts. Minimum output voltage is 13 volts. According to above calculation. Hence, voltage difference across. Hence, voltage difference across. Zener diode is always greater than 8 volts. So, Zener diode functions effectively. So Zener diode functions effectively. So likewise, have complete answers. Write complete answers. Otherwise, don't write incomplete like here and there answers. Right. Part 3. Calculate the minimum capacitance value required to ensure smooth voltage never drops below 8 volts. Calculate the minimum capacitance value required. Right. Then for that, calculate the minimum capacitance value required to ensure smooth voltage never drops below 8 volts. Right. Which means minimum voltage that could go up to is 8 volts. No? If it never drops below 8 volts, then in this curve, right? In this curve, right, as 13 volts. Now, if it could go up to 8 volts, right? If there is never going to drop beyond 8, right? Minimum value can get is 8 volts, right? Minimum value is 8 volts. Then, if there is 8, say part 3, right? Part 3. Calculate the minimum capacitance. Yeah. Part 3. Then voltage difference. That voltage difference is the ripple voltage here now in the new circuit. Right? Now this voltage difference will be the ripple voltage in the new circuit. Now if this is 14, right? If it is not going beyond 8, then new ripple voltage is going to be 14 minus 6. Then VR equals 14 minus 8. That is 6 volts. Right? That is 6 volts. And the equation was given to us. VR equals IL over FR, right? FR, IL over FRC. Now VR is 6, right? And IL is unchanged. 0.02. Frequency is unchanged. 100 C. Then from this, I have to find C. So C is given by 600 here over 0.02. Right? 600 over 0.02. 600 over 0. The other way, right? 0.02 over 600. 0.02 over 600. Then 0.02 over 600. Right? Simplify. 0.02. 2 over 6 is 1 over 3. No? Then 600, 10 to the power minus 10 to the power 2 here. Then altogether 10 to the power minus 4 here. 10 to the power minus 4 here. Then this is 0.33, which means 33.3. You can keep it in microfarads. 33.33 microfarads. Right? So likewise, now we are using the same given equation. In this required manner. Right? Now, always, if there are any arguments to be mentioned, right, you have to mention all these arguments properly to the point. Right? If arguments are to be mentioned. Fourth, determine the range of resistance values of the safety resistor Rs should have so that the Zener power does not exceed 1.6 watts and 8 volts output stays in regulation with 400 ohms load. Take minimum Zener current as 5 milliamperes. Right, now RS is here. Right, now after this point we know what happens is, right, if this incoming current is I, say this current is IL, right, and through this Zener diode another part of the current flows, that is IC. Then it is like I equals IC plus IL, right? Kirchhoff's laws. Right, that is capital I equals IC plus IL. Right, now first part is about right, Zener diode power does not exceed 1.6. Zener diode's power does not exceed 1.6. Does not exceed means that is the maximum value, no? That's the maximum value. Then if we find the maximum current, we know P equals VI. Right, if I need max, then P max, right, equals, this is V max, right, and I max. P max is 1.6, no? 1.6. V max is 8 into I max. Now from here, maximum current through Zener diode can be determined. Then I max is 1.6 over 8. 16 over 8 is 2, then 1.6 over 8 is 0.2 amperes. Right. Maximum current through Zener diode is 0.8. Right. Now what is asked? Determine the range of resistance values for RS. Then through RS, do we know the current flow through the RS? Do we know the current flow through RS? We know, because I is given by IC plus IL. right? That is given by IC plus IL. So we know for the maximum current, the minimum resistance occurs. No? For the maximum current, the minimum resistance occurs. For the maximum current, the minimum resistance occurs. Right? So we know potential at this output here is, right? It was potential at the output. Potential at the output was 14. Then see, you have to identify these values. Then this must be 14. This must be 14. And this is grounded 0. Then this point is also grounded. If this potential difference is 8 volts, then this is at 8 volts. Right? Which means potential difference across RS is known. Potential difference across RS is known. Right? ඒක දන්නවා. එහෙනම් ඉතින් if you need to find a resistance, if potential difference and currents are known, apply delta V equals IR. Right? Then for the maximum I, minimum R comes. For the maximum I, minimum R comes. Right? Then for RS, for RS, delta V equals IR. Delta V equals IR. Right? Then delta V is 14 minus 8. 14 minus 8. And I here is right 0.8 flows as Imax, that is through the Zener diode, and another 0.02 IL was determined before, 0.02 flows as IL, right? Then you have to add both together, then 0.2 plus 0.02, right? Because this is the reason, right? This is the reason. From Kirchhoff's laws, you know, right? From Kirchhoff's laws, you know, I is given by IL plus IC, right? I is given by IL plus IC, right? So I use it here. Then this is 6, and here R min comes. Maximum value, minimum resistance. Then this is 0.202 times R min, a small simplification. Then R min comes as 27.3 ohms. Right? Minimum R is 27.3 ohms. 27.3 ohms. Alright, 27.3. And then we need to find the maximum value also, right? Maximum value also. Then maximum value occurs when the minimum current flows through Zener diode, no? Maximum value occurs when minimum current flows through Zener diode. Then minimum I is, right? Similarly, now as I found this I, now minimum I is, right? Minimum current flows through Zener diode is, it was given here, it was given as 5 milliamperes, right? Then 5 milli means 0.005, no? Right? 0.005 plus load current 0.02, right? 0.02. Then minimum current here is 0.025, right? 0.025. Then again delta V equals IR for RS, delta V equals IR, right? Still delta V remains same because points are same. This is 14 minus 8. And I is this one now 0.025. R is for the minimum current, maximum R max comes. For the minimum current, maximum R comes. Then R max equals 6 over, right? 6 over 0.025. 6 over 0.025, right? That is 240 ohms. That is 240 ohms, right? That part is also done. That is 240 ohms. Right? Now what was asked from us? Right? That was about the range. Range determine the range of resistance. Then you have to mention the range. Therefore, range is, right? It varies from, now the minimum value was 27.3, right? Minimum value was 27.3, maximum is 240. Then 27.3 sorry 27.3 ohms greater than RS 240 ohms, right? This is the range. That is in between these two, 27.3 and 240. That is in between 27.3 and 240. In between 27.3 and 240, right? Range is known, right? See how these logics are used, right? My logics are used, and the question is totally different from diodes. Normal PN diodes, and Zener diodes, right? So still it is drawn. It is going with the diodes. Part D, right? Part D. Part D. 1. D1. If the diodes are not ideal and forward biased, voltage drop is 0.7 volts, what will happen to the triple voltage? Right. If these diodes are non-ideal, we know. 1 second. Right. We know in the full wave rectifier, right? Even though there are 4 diodes, only 2 diodes are working at a time. No, only 2 diodes are functioning at a time, right? Current when this point x is plus, or right, when this above point x is plus, see, when this above point x is plus, right? How current flows is like this, and only this diode is forward biased, and it flows through this, right? Flows through this, and flows through these two, and comes here up to this point, and then this was reverse bias, so it goes through this, right? It goes through this, and here, and it completes like this. See, only 2 diodes, these two are functioning now. So likewise, even if x is minus, if that point is minus, even if that point is minus, right, there will be only 2 diodes which are functioning, which are activating. Then if 2 diodes are activating, there are 2 voltage drops, right? About these voltage drops we discussed in the theory class, right? About these voltage drops. In full wave rectifier, there are 2 voltage drops. In half wave rectifier, there's only 1 voltage drop. In full wave rectifier using centered up transformer, there's only 1 voltage drop, right? We have 3 different rectifier circuits, right? We have 3 different rectifier circuits: half wave rectifier, and full wave rectifier using bridge circuit, that is this one, and the other one, full wave rectifier using centered up transformer, right? That is the other one. And in the centered up transformer, there's only 1 voltage drop, and in this one bridge circuit, there are 2 voltage drops. Then what happens is, if there are 2 diodes are going to function with 0.7 voltage drops, right? With 0.7 voltage drops, then altogether, if 2 diodes are functions, 0.7 into 2, this voltage will be dropped from the final output. This voltage will be dropped from the final output, right? Then the question is, what happens to the triple voltage, right? What happens to the triple voltage? Then about triple voltage remains same. Triple voltage is the difference, no? Triple voltage remains same, but what changes is the maximum voltage or the peak voltage, right? Then if the diodes are not ideal, what will happen to the ripple voltage? By how much will the peak value of the smooth DC voltage change, right? Then first about ripple voltage, no? Ripple voltage is unchanged. Ripple voltage equation again, ripple voltage depends on that equation, right? Then ripple voltage is unchanged. Ripple voltage is unchanged. Ripple voltage is unchanged, right? But peak voltage, is dropped by 1.4 volts, right? It's dropped by 1.4 volts, right? Drops by 1.4 means it drops up to 14, right? 14 minus 1.4 is it drops up to 12.6, drops up to 12.6 volts, right? This is what's happening. Because 2 non-ideal diodes are activated now. 2 non-ideal diodes are activated. They absorb 2 voltage drops, right? They have 2 voltage drops. Second one, how does a Zener regulated DC voltage respond when a load resistance is decreased? When the load resistance is decreased, right? Now the thing is, right? Now the thing is, what is going to change? Zener regulated DC voltage respond when the load resistance is decreased. Now, main feature about a Zener diode is Zener diode does not change its Zener voltage even though the current through Zener diode changes. Right? That's the main feature of a Zener diode. Even though the current through Zener diode changes, VZ Zener voltage is unchanged. That's the unique feature, most unique feature about a Zener diode. Right? Which means now even though the current changes, right? Even though the load resistance changes, when load resistance changes, current changes. Right? Then IZ will also change, but yet VZ remains unchanged. That is the most important feature and the unique feature. Important means unique feature about a Zener diode. Then this is what happens in the circuit, right? This is what happens in the circuit. In the circuit, right? When RS changes, right? IL changes. RS මොකක්ද කරන්නේ decrease කරනවානේ. RS decreases. See, when RS decreases, right? When RS decreases, right? IL increases. When IL increases, IC Zener current decreases. Right? Zener current decreases. Right? But right, VZ is unchanged. But VZ is unchanged. That's the unique feature about the Zener diode. Right? But VZ is unchanged. Then the question is, how does regulated voltage respond? Then you have to explain this. For the load resistance when decreased, then you have to explain this way. Explain this in words. When RS decreases, IL increases. Hence IC means Zener current. Zener current decreases. Zener current decreases. Right? But Zener voltage remains unchanged across the Zener diode. Right? That's the most important feature about a Zener diode. Right? Zener voltage remains unchanged across the Zener diode. Right? That's it about that question. Right? That's it about that. Right. Listen now. I will keep question 2 as a homework, so you can try it later. Right? You can try question 2 later. Right? That is also like basically that is from op amps and flip flops.